Before we get back into NMR, we are 1 week away from our midterm exam, so I want to talk about expectations on the cheat sheets. Do you guys remember what some of the expectations are? What you're allowed, what you're not?
Handwritten.
Handwritten cheat sheets. One-sided sheet of paper. I would say printer paper size. One of my OChem 2 students this morning told me that that means A4. I don't really know. 8.5 by 11?
Yeah.
Sounds great. But I know that some notebook pages are a little bit different size. I actually had an OChem 2 student a few semesters ago who said, I don't want to bring one sheet. I want to break up like each chapter or each unit onto a note card. So can I use this many note cards because it has the same amount of surface area as the one-sided sheet of paper?
He said, no, the boiling point is different.
Right. You're right, because actually there is more surface area on the edges. But I'd be fine with it. So whatever you guys want to do, some notebook pages are a little bit bigger, a little bit smaller. And I really don't believe that a few square centimeters difference in area is going to be the difference between one student doing well and one student doing poorly. But you're right, the other expectation was that it was handwritten. And I know a lot of you take notes on tablets. And I understand that taking notes and writing the stuff out on your tablet is handwriting it, but printing it from the tablet is not as easy to keep consistent because you can change the font sizes or condense it, expand it, whatever. This also means no images, so no screenshots from online. You see something online that's a good resource for you, copy it down onto your cheat sheet. And the last expectation I want you guys to have is that you keep it. One of the reasons I encourage you to make a cheat sheet is because when you leave OChem, that's basically going to be your cliff notes on it. What are the most important reactions, terminology, concept, examples that you want to walk away from with your OChem 1 experience? I don't need it. I think it's going to be more beneficial to you than me. The last thing that I would encourage is that you make it multiple times. The students that don't use their cheat sheet during the exam often do the best on the exams. And the reason they don't use it is because they didn't make it once, they made it twice or 3 times. Each time revising, I don't think I need these examples. I think I need better examples for this. I think I can expand this region more so that it's easier to read through it. The students that spend the most time looking at their cheat sheets often do the worst on the exam. They made it the night before, they don't know what's on it, they didn't think through their examples well enough, and then they feel dependent on this crutch that isn't actually helping them do well on the exam. So I'm going to be quite honest here. If you're going to make this the night before, maybe don't even make it. Make it tonight, and then revise it Wednesday, and then revise it Saturday, and then look at making it again Tuesday night before the exam. This is a risk, not an advantage, right? Keep that in mind. All right, any questions on the cheat sheet for next week's exam? You guys know where we're meeting for the exam? Right here, 10 a.m. Our exam will start at 10:05 sharp, and you guys will have 90 minutes, and that will take us through the rest of the class period.
What's the most missed part of the exam?
It's a good question. Like, what concept is missed?
Yeah.
I don't know. It's really a range. I want to say maybe the electron arrow pushing, since that is a challenging aspect. There's one question on showing arrows, one question on predicting products from arrows. And they're very easy. They're pretty.
So if an arrow points to a bond, that bond breaks, right?
No, arrows.
If an arrow points from a bond to an atom, that bond breaks and the electron gets the atom.
Correct. If an arrow points from a bond, that bond is breaking. And wherever an arrow points to, a bond is forming or a lone pair is being taken. There's kind of two options there. And next week, Tuesday, is a review day for our midterm. So this weekend you have a unit test on Unit 3 spectroscopy. Tomorrow, we should be done with NMR today. Tomorrow will be a review day for Unit 3 to prepare for your unit test. And then Tuesday will be a review for Unit 1, Unit 2, and Unit 3. So if you have questions, next week, Tuesday is the day to bring them in. I actually won't have much review material prepared. If you guys don't have anything, I'll just pull up the practice midterm and have you guys look at that. But come with specific questions next week, and we can do examples and prepare for your midterm.
Is there like a study guide, or is that practice midterm?
Do you know what? I will look more to see if I can make a study guide for you. It might have to be this weekend. I had a study guide for one of my midterms, and I couldn't remember if it was my OChem 1 or OChem 2. And it was like literally a title document, and nothing else was on there. So yeah, I don't have one. I'll look at making one this weekend after I've finished making both of my exams for next week. But I would say the practice or the midterm questions are really good. What I might actually do is just take the title of your midterm questions and write them out, and that is your study guide, basically. Those are all of your main concepts from the unit tests. I know we don't have a lot of time, like this class being 3 days a week and having only Tuesday as a review day before our exam on Wednesday. But you will finish your unit test Monday night at midnight. I'm going to have this midterm exam review publish on, no, not right now. I'm going to have it publish the morning of Tuesday next week. So after you have finished the Unit 3 test. And then any concepts from Unit 1, Unit 2, or Unit 3 that you need more time studying, you'll be able to go to that midterm exam review, and you'll see all of the unit test questions, including the ones you had and the ones that you did not have, so that you can get more example with questions or concepts that you feel like you struggled with. I know that only gives you like 1 day to use it, but it is a challenge with having the unit test fall so close to the midterm. Okay, anything else you guys want to discuss before we get back to NMR? All right. So the first of 3 very important concepts for us we're going to look at the chemical shift of a signal. The chemical shift was also the name of the x-axis. So we're basically saying where along the x-axis does a signal appear, and that chemical shift can help us approximate functionality. And I'm saying approximate because some functional groups are actually pretty easy to detect based on their chemical shift. Many functional groups overlap, and yet you can still learn that there is some functionality based on a chemical shift. This is my NMR correlation table. There are not many like it. Mine is one of the most condensed correlation tables for NMR that you'll find out there. If you are interested in practicing spectroscopy a little bit more and you want to look at things that don't look like my work that you find down here in the old study materials on spectroscopy, and they don't look like active, then I encourage you to come to the bottom of Unit 3, do this PLO4 spectroscopy bonus assignment. Remember, this just goes towards your homework category. This is made by our course lead, Ron Valcarsi. He has his own website. And on his website, you will find his own correlation tables. So this is his NMR correlation table. What you'll notice about his is that it tells you the expected chemical shift, delta, for the hydrogens of a methyl group when they are adjacent to a carbon, adjacent to an allylic carbon, adjacent to a carbon bonded to an oxygen, when the methyl group itself is allylic or connected to the alkene, when it's connected to an aromatic ring, when it's connected to a carbonyl, when it's connected to an aryl carbonyl, when it's connected to an amide, when it's connected to an alcohol, an ether, an aryl ether, when it's connected to the oxygen of an ester. Every slight variance in the functionality, every slight variation in the chemical environment changes the expected chemical shift. This table is not set up by increasing chemical shift. As you can see in that right-hand side of this column, chemical shift is kind of going up and down as you move through this. But it's pretty comprehensive. Almost every environment that you can expect to find a CH3, a CH2, a CH, all of their expected chemical shifts are present. Then there's this second table, which is a kind of a calculator. It says if you've got a CH2 and one of your X groups is one of these and your other X group is one of these, then you can plug it into this equation and you can predict the chemical shift. That means that if you have a molecule and you know its chemical environment, you know its chemical structure, you can make an estimated calculation for where every single signal for every hydrogen will show up. And then you can look at its NMR spectrum and you can more easily map every signal to every hydrogen. But we're not going to do that. That would be, in my opinion, for a spectroscopy course or an advanced organic chemistry course. This, in my opinion, is just a bit too involved. It's too in-depth for our course. You can see that he keeps going down. He shows some alcohols that are, hydrogens that are not attached to carbons, but attached to other groups. This is his IR correlation table. You can see that his is based on bond type and not necessarily organized by frequency range. Then he has this carbon NMR correlation table. His carbon NMR correlation table maybe looks a little bit more like my proton NMR correlation table. But there is one other correlation table for NMR that I'd like you to see. If you open up these section 13 lecture slides. And you scroll down to this page on NMR. This is an old version of my correlation table. You'll notice there's some differences. But this yellow correlation table comes out of our class textbook. This is the correlation table for proton NMR, HNMR, that comes out of the Francis Carey textbook. So it's more comprehensive than my correlation table, but it's less comprehensive than Ron's correlation table. Kind of fits the middle ground. It tells you what environment your hydrogen is in specifically, but then it gives you a range of where that's showing up. And it doesn't necessarily give you an exact prediction. I encourage you to get to know this correlation table because it models the correlation table that you're going to see on the midterm exam. The only thing that's different is that all of the words here are taken out when I give it to you on the midterm exam and on the final exam. Similarly, I want you to get to know this IR correlation table. The only difference is this far left-hand column does not show up on the midterm and final exam. So you get some description of the bond, but you don't get visualization of the bond. And then vice versa for NMR, you get some visualization of the hydrogen environment, but you don't get names for the hydrogen environment. So this is chemical shift. Coming back to this idea of approximating some functionality. Let's start on the far left-hand side. Upfield or downfield? Yeah, downfield. Downfield, we get this region from about 9 to 12, where hydrogens connected to aldehydes or carboxylic acids, their signals generally show up. So if there's a signal in this very downfield region, you can anticipate it's the signal of an aldehyde or a carboxylic acid, although you wouldn't be able to distinguish which one necessarily. So if you had the NMR and you had the IR, then you could couple them and say IR shows an aldehyde from the CO double bond and the CH of the aldehyde. NMR confirms because there's a signal in that region.
Are there any nitrogens in NMR?
Yeah, you'll actually notice alcohols and amines don't show up on my little correlation table. And that's because their ranges are pretty chaotic, but I'll actually talk about it in this section. But to answer your question, this correlation table is not looking at carbon, it's not looking at oxygen, it's not looking at nitrogen. This is looking only at hydrogens. These are signals produced by hydrogen nuclei. But what the hydrogen nuclei is bonded to affects its shielding, and that shielding affects its chemical shift of its signal. So when we're approximating some functionality, there's one region that helps us identify carboxylic acids and aldehydes. That's my abbreviation for the aldehyde. Do you know what? I could give a better abbreviation for the carboxylic acid as well, which is that CO2H. Can't tell them apart, but I know it's a hydrogen from one of those two. We can also approximate aromatic rings, give or take. Sometimes other signals show up here, but aromatic rings have this nice region, generally from 6.5 to 8.5 ppm. If I have a signal in this region, I have a pretty good idea that there's an aromatic ring in the compound. And how would I confirm it? Well, the best way to confirm it is to look at the IR. And the IR tells me that there's sp2ch aromatic overtones, CC double bonds. But a signal in that region, pretty good indicator for an aromatic ring. Then we get some approximation of alkenes. These like to absorb around 4.5 to 6.5. And you'll notice my boxes here on this correlation table, they overlap a little bit. That can be a challenge. The hydrogen of an alkene can sometimes show up in the same region as the hydrogen of an aromatic ring. That actually should remind you of how similar alkenes and aromatic rings show up in the IR. Both of their sp2ch bonds show up in a similar range. Both of their CC double bonds show up in a similar range. In NMR, alkenes and aromatic rings are actually more distinct than they are in the IR. So NMR can be a better way than IR to distinguish alkenes and aromatic rings. I'm just going to try to highlight that. If I just say better than IR, does that make sense to you guys? All right, then I've got this, this range that I'm calling functional group adjacent. These are hydrogens that are bonded to the carbon of a functional group, so they are kind of hydrogens adjacent to the functional group itself. Or they are bonded to a carbon that is adjacent to a functional group. So I do want to give a couple of examples because I feel like this can be a bit confusing. Okay. Just a big molecule, but it gives us a lot of things to think about. Functional group adjacent here. I'll give you guys a second because I know you're copying it down. Well, some of the functional groups that I see are alkene, aromatic ring, ketone, and ether. So this CH2 on either side of the ether, functional group adjacent. Those hydrogens are adjacent to the functional group. And notice that they look a lot like this hydrogen. They're bonded to the carbon that is bonded to an oxygen. This has a little bit of nuance to it, this structure. I'm actually indicating that the hydrogens bonded to the carbon that is attached to oxygen show up further to the left than hydrogens bonded to the carbon that is bonded to a carbonyl. So these sets of hydrogens, they should show up a little bit more left in this region. The closer you are to that electronegative atom, the further left they move because they're more deshielded. These hydrogens are also functional group adjacent. They look a lot more like this hydrogen, the one that is adjacent to a carbonyl. They're further away from that electronegative atom. Their deshielding is a little bit less. I would expect these signals to show up more to the left, more downfield, than this signal. Then I've got these two hydrogens here, which are adjacent to the aromatic ring. I would expect them to be in that functional group adjacent range. I've got these two hydrogens that are adjacent to the alkene. I would expect their signal to show up in the functional group adjacent range. Now remember, you want to figure out exactly where those signals are showing up. It's not impossible. You just need to find a correlation table like this and say, I've got a CH2. On one side, I have a CH2 group, and on the other side, I have an alkene group. So actually, I can't calculate it from this, but maybe I come up here and I find a CH2 that has a carbon on one side and an alkene on the other. And now I've got a more specified prediction of where that shows up. Shows up at 2.3. The reason I do this is because it's not always useful in the ways that we're going to use NMR to calculate specific chemical shifts. It's actually a little bit better to just say, I know that this is next to something else. And again, the closer it is to an electronegative atom, the further left it's going to go. The further it is from an electronegative atom, further right it will be in the range.
So, how come the hydrogens adjacent to the ether are more de-shielded
Yeah.
than the one just to the right of them?
No, I would say that these hydrogens are also de-shielded as much as these.
You said no. Those two compared to that one.
Well, this one is further from the electronegative atom.
But isn't it also I guess it's 2 atoms away from the oxygen.
Yeah, if you think about the hydrogen position, HCO, oxygen is pulling on those electrons and de-shielding the H. Here I've got HCCO. So that oxygen is de-shielding the hydrogens, but a little less effectively. And then think about your carboxylic acids and your aldehydes. HCO with the double bond, this hydrogen is highly de-shielded. HOCO double bond, highly de-shielded. Once again, a little nuance in how this is laid out. The signal from a carboxylic acid generally shows up further left. Signal from an aldehyde generally shows up further right.
And so you're gonna be like de-shielded from this one, but it could also be like less shielded from the other one.
Okay, actually, I'm not sure if I understand you right, but I am going to get to an idea of compounding effects, how multiple functional groups show up,
Okay.
how they affect that.
I guess I'm kind of comparing those 2 hydrogens just to the right of the ether.
Mm-hmm. To
Relative
these two.
to that oxygen versus the other oxygen up there to the right.
Okay, yeah, so these 2 signals, this one signal for these 2 hydrogens likely does show up further left, more downfield, than this signal.
Mm-hmm.
Because you're right, it is equally as close to the oxygen, but it's closer to a carbonyl.
Mm-hmm.
So their chemical environment is different. They're not equivalent to hydrogens. They're not going to give the same signal. And there is one group of hydrogens that I didn't label, which was the CH3 group down here, which I'm not calling electronegative adjacent, functional group adjacent, because it's not adjacent to an alkene, an aromatic ring, a ketone, a heteroatom. So the signal from this CH3 group, I don't expect it to fall in this range.
So also, is that the same reason you didn't do that other hydrogen up next to the alkene?
Well, there are 3 hydrogens here, and they're all vinylic hydrogens. They're all attached to the alkene. So I would expect them to fall into this range.
Okay.
And I didn't label any of these hydrogens
Because they're in the aromatic ring.
because they're in that aromatic region. Exactly. So I want to answer Hayden's question first, and then we'll do Brett and Carly.
Yeah, so it seems like the trend for ppm downfield is the impact priority. Is that pretty solid, or is that just like convenient?
Convenient. Coincidental. Yeah, no relation to the priority of functional groups in the IR. Brett, I think I saw your hand.
Wouldn't the CH3 on the far left, wouldn't that be like an alkane?
Yes, it's more closely related to alkane,
Okay, so
and that's the one group we haven't covered yet.
okay, so you wouldn't count that as like a functional group adjacent?
Correct.
Okay.
It's not bonded to any heteroatoms. It's not bonded to any carbonyls. It's not bonded to any other hydrocarbon groups.
Oh, because
It's just bonded to a CH2.
Okay.
Mm-hmm. Carly, you got a question?
Yeah, where is the chart where it shows like all the different ones? I guess when you scroll down, or is it a different,
Oops.
where it shows like whether or not like a CH2 is like 0.5, like,
Are you talking about this one?
yes, is that on Canvas?
Yes and no. If you go to the PLO,
Oh, it's in the
no, it's not. If you go to the PLO, it links you to Ron Valcarce's website,
Oh, and that's where it is.
and this document is linked on his website, so you can access it there. You can also Google. I mean, let's just see if this actually works. Comprehensive NMR correlation table, and you'll probably find a lot of similar things. They give, well, this one I guess gives you ranges. Here's CU Boulder. They're giving you, again, ranges, but maybe with more specific things. I had a professor in college who had a website of his own. I wonder if he still has it up. No, I don't think so. So he had a, oh, bummer. He had a website that had literally a calculator that you could plug in what your different groups were around your hydrogen, and it would spit out the predicted chemical shift. I don't think this would be it. Oh, bummer. I think that's probably his website and he lost it. Anyways. Okay, other questions? Okay, so we get this idea that what your hydrogen is in, what chemical environment it's in, dictates its signal. The last one being, if it's mostly just alkane, it's going to show up in this low frequency range, like 0.5 to 2 ppm. And it's actually, again, the shielding and de-shielding makes quite a bit of sense. Hydrogens that are part of a CH3 group show up closer to 0.5, and hydrogens that are part of a CH group bonded to a bunch of other things. Yeah, this isn't what I want to show. This hydrogen is more de-shielded. It's got carbons around it that are pulling the electrons away from that hydrogen. More de-shielded, further left signal. Cameron.
I think you said this yesterday, and if it's irrelevant, it doesn't really matter. I'm sorry, but like, what does the unit parts per million mean? Like parts of what per million of what?
Great question. What does it ever mean? I guess we usually use it in concentration to mean parts of pollutant, parts of analyte, parts of standard, per million parts of solution. But what we're saying here is frequency rather than concentration. So we're saying maybe every time I measure 1 million seconds, I get one signal. One signal or one wavelength per million seconds. I'm not quite sure, and I don't have a best answer for you, but it is being used here as a unit of frequency. Specifically, we're looking at radio wave light that is coming out, but it's radio wave light not being represented with its frequency in hertz, but being represented relative to TMS, tetramethylsilane. The signal that TMS gives off is called 0 ppm. So I guess maybe you could say it's how many parts per million you have per million signals of TMS. That might be a good way to think about it.
And so with, on the functional group adjacent, the two hydrogens that were on the far left, you said they make the same signal. If there was only one of them, is that going to change the reading on the chart? Because the same signal is being made multiple times?
So these two sets of CH2 do not make the same signal. They are unique hydrogens. They're in a similar chemical environment where they're both bonded. The hydrogens are all bonded to a carbon bonded to O. But this CH2 group is adjacent to a CH3 as well. And this CH2 group is adjacent to the CH2 of a ketone. So their signals will be similar, but not the same. And this does get me into the next point, which is even unique signals can overlap, which means we don't always get a good idea of how many unique signals are truly in a molecule. Yesterday we went ahead and looked at, what did we look at? Meta-hydroxytoluene, I think. And we looked at how many, oh no, it was a styrene. We looked at how many unique signals that we would expect. I don't know why it doesn't like me. All right, give me a second. C6H. Okay, I guess they.
C8. I don't know if you meant to say C6.
No, C8. I was looking for the vinyl group, but they don't have it. So I'm gonna have to just do. I'll just have to do something different. Let's think about this molecule. Oh, it's really not what I want. I would love a different one. Sorry, guys. This is an interesting thing. Not every molecule has its NMR or IR spectrum taken. So here's an example aromatic ring. It's not the same as the example I had yesterday, but there's the hydrogen of the aldehyde, the hydrogens of the methyl group, and each of these individual aromatic hydrogens are all different from each other. This hydrogen directly adjacent to the aldehyde and a hydrogen versus this hydrogen adjacent to a hydrogen, but adjacent to the methyl group as well. There's no symmetry in this molecule, so every hydrogen is different, except for the CH3 groups, which are all the same. But, so what, that gives me 4 different hydrogens, plus the methyl group and the aldehyde, so that's 6 different signals. Man, this is a bad example, because actually when I look at the aldehydes, when I look at the aromatic region, I get an individual signal for all of them. And that's not what I wanted to show you. So instead, I'm just going to show you toluene. Toluene has just a methyl group coming off of it. So here's that methyl group at the top. Now there is symmetry in toluene straight down the middle, but I should still say that these hydrogens give one signal, these hydrogens give a second signal, this gives a third signal. So I would expect 3 signals in the aromatic region, 1 signal in the electronegative adjacent region. And when I look at its NMR, how many signals do you see? Looks like 2. There's a lot of stuff going on down here in the aromatic region. But what's happened is that those unique signals in the aromatic region are just forming a cluster. They are unique. They're in different chemical environments. But for one reason or another, their chemical shift is still close enough that they overlap. So this, I guess, is our best example for this. Here's toluene. And although we would expect to find A, B, C, A, B, and then D, when we look at its NMR, we just find 2 signals. And what we have here is A, B, and C all showing up together. Is that okay? And then lastly with chemical shift is multiple groups can have a compounding effect. So, there's not much that you can do to take a chemical shift to be further to the right. In order to get it further to the right, you just need more alkane character. But there is a lot you can do to shift further to the left. So I want to look up a compound called chloroform. Chloroform is often used as a solvent in NMR. This is CHCl3. We deuterate it often before we use it as a solvent so that the hydrogen doesn't produce a signal. Now that hydrogen you would probably say is functional group adjacent. It's a hydrogen bonded to a carbon of an alkyl chloride. And given that the hydrogen is bonded next to an electronegative atom, similar to this O, I would expect it to be on the further side of the functional group adjacent, further to the left rather than further to the right. If you look at your textbook's example, they tell you that the hydrogen bonded to the carbon of an alkyl chloride shows up in a range of 4.1 to 3.1. But they don't explain what these other 2 bonds are. So what happens if it's one of those other 2 bonds? Ron's correlation table has that calculator. If you say that the CH starts with a shift of 0.23, and then you add chlorine 3 times for each of those positions, 2.5, 5.5, 7.5, plus 0.23, that's 7.7 something, 7.73. And here's what we actually get. The hydrogen of chloroform produces a signal at 7.26. Always exactly at 7.26. Excuse me, I rounded too much. 7.256. So that's the compounding effect. This hydrogen is not just electronegative adjacent or a functional group adjacent. It's basically functional group adjacent 3 times. And so each time it's adjacent to a functional group, its signal gets shifted even further left. What is that region? If you saw a signal there, what would you expect?
Aromatic.
You'd think that signal is produced by an aromatic ring, but it's not, because it has a compounding effect. Here's another one. Here is an aromatic ring with a vinyl group attached. And Hayden, I saw your hand. I'll get to you in a second.
Is that alkyl halide? CHCl3?
Alkyl halide, yeah. But again, the alkyl halide range that you might anticipate, functional group adjacent, isn't what you get because it's adjacent to that 3 times.
Yeah, so back to the example of the chlorine, notice like the hydrogens were assumed even though it had open lone pairs, but on the last example, the oxygens, we just assumed they were there. Is there a reason why? I thought it was pretty electronegative.
Can you say that one more time?
Yeah, like the last example where the hydrogens weren't explicitly there, but we assumed they were there on the edge of the bond. Notice we didn't do that for the one with chlorine.
Are you talking about this?
Yeah, or No, it was the one where I think Jamie asked, and it was on the side, and it was like the terminal, and there were two hydrogens. Oh yeah, I can't see it. Yeah, that one. Yeah. Oh, to the very right. Yeah. So how you assume like those were there? Would you do the same for that example there?
2 hydrogens.
Like a
One hydrogen.
CaCl3. Would you assume hydrogens are attached to the Cls?
No. But if this is a very small molecule, so it's hard to do like a bond line structure for it. But if we expand its Lewis dot structure, first of all, hydrogens to heteroatoms can never be assumed. You can never write OH as O. You can never write NH2 as N. You cannot assume hydrogens on heteroatoms. It's one of our rules of bond line structure. Then, if these did have hydrogens and we showed them, you've now got 2 bonds going to each of those chlorines. And 2 bonds to chlorine makes a positively charged halogen. So, definitely, no.
That makes sense.
Good question.
Carbon's organic, so you would just assume that they're there.
Yep. Okay, I thought this example was maybe going to be a little bit more relevant to us, but we've got another situation. Notice here that they're saying all 5 of these aromatic hydrogens are giving the same signal. They've labeled them all with A. Even though when you look at that region, this signal looks very complex, almost like it's multiple signals overlapping with each other. And we know that there is symmetry in this structure, but these 2 are the same, these 2 are distinct, and this third one is distinct. So why they labeled them all as A? Don't know, they maybe got lazy. Then we look in the vinylic region, and lo and behold, we've got signals for the vinylic hydrogens, some of them much closer, maybe even creeping into the aromatic region. But because we know that we're expecting that to be kind of compounded, it's a hydrogen that is vinylic and adjacent to the functional group. We're not totally surprised. Now you look at the number of signals as well. It looks like there's 1, 2, 3, 4, 5, 6, 7, 8, and a cluster. But there are not even, no, there are that many hydrogens here, but they're not all getting their own signal. So, complex. It gets messy. You've got to be a little bit okay with waving your hand at this stuff again, because there is good information to pull out, but you don't want to think that you would stake your life on it. Yeah? All right. Questions about the chemical shift aspect?
I have a question about the solvent. Is it used for both the proton and the carbon?
It can be, yeah.
So why would you use that solvent for the carbon one? Like, would that be his?
There is only one solvent that you maybe could use for carbon-13 NMR that doesn't have a carbon in it, and that's water. But otherwise, chloroform, acetone, dimethyl sulfoxide, DMSO, all of those other common solvents, they all have carbons, and they're all going to produce a carbon signal. The issue is you can't really avoid it. So oftentimes what you do is look for it. You know where that signal from the solvent will show up. So you can look for it and identify it. In fact, this is really common when you use chloroform as well. We deuterate it, but it's not 100%. So there's some CH-Cl3 every time you use chloroform as a solvent, and then you run a sample and you get an IR, or you get an NMR spectrum that has a line right at 7.26, that's your solvent. And you know it's your solvent because we know where chloroform shows up. And I kind of cut you off. What were you?
No, I was gonna, is it usually always that 7.26 then?
Right,
Is that how we
so
know that's the solvent then?
when I would run NMR samples in college or in grad school, I knew what solvent I was using, and I had a big table of chemical shifts from common solids. And you just know where you're looking for those chemical shifts so that you can ignore them. Jamie?
Could you just clarify real quick? How come, so on that methyl cyclohexane, we see all the hydrogens in the aromatic ring overlap in one peak?
Methylbenzene.
Sorry, yeah. Why don't we see the exact same thing here just for an alkene, or for an alkene?
No, I'm sorry. Say it one more time.
If all the signals in the aromatic ring overlap into one peak there,
Yeah.
with the one for the methyl group on the right side, why don't we see the same thing over here just with an alkene?
Because these hydrogens are not the same as each other.
Okay.
These two hydrogens are locked in their positions. So we talked about this a little bit yesterday. This hydrogen and this hydrogen are very close, but this hydrogen and this hydrogen are very far away from each other.
So you get two different hydrogen signals from those two.
Yep. And a different hydrogen signal from this.
Okay.
There is a good question to be asked of,
Why are the aromatic ring peaks overlapping there?
get comfortable with it. And this is really the best I can say is it's not always predictable when signals are going to be different and when signals are going to overlap.
Is there any reason why it didn't overlap this one at all?
It's chemical environment.
So okay, just like the existence of the alkene made it so it did do that. Probably.
All of the aromatic signals did overlap here.
Don't we have stuff beyond 6.5, which is where the alkene functionality would end?
About.
Or
But
I
again,
guess
we're looking at compounding effects. So the alkene being adjacent to the aromatic ring
it does have some wiggle.
pushes, it does. It's not a hard and fast. In fact, that's one of my issues with this calculator.
So that is an overlapping peak that we're looking at there.
In the aromatic region,
That is overlap.
right here.
Okay.
Yes. Although SDBS would tell you all of those aromatic hydrogens are equivalent to each other, which is not true. They are in different chemical environments. There are
Yeah.
3 types, but their signals are overlapping. Do you know where else this happens? Overlap is on alkane structures. So let's look at 2-methylpentane. And let's look at its NMR. I think we looked at 2-methylpentane yesterday, and we said that 2-methylpentane has 5 distinct hydrogen environments: A, B, C, D, E. So I should expect 5 distinct signals. But quite honestly, I've got a signal here furthest to the right that is pretty easy to tell apart, but it physically is joined at the bottom. The signal never goes back down to baseline. With this next peak, and I feel like I can tell this peak apart from this peak, but they're all overlapped. Their chemical shifts are distinct, but not distinct enough. All right. Moving on from chemical shift, we're going to talk about integration. Integration is proportional to the number of hydrogens producing a signal. Maybe I should say the signal, because we are talking about signal integration. So, how many hydrogens produce that signal? Remember, we're talking about unique signals, equivalent sets of hydrogens, identical chemical environments. Let's take this example, 2-methylpentane, again, which we said has 5 distinct signals. Is it easy to tell those signals apart? No. But we don't need to tell those signals apart to be able to do this analysis. in the theoretical world where we can tell those signals apart, the question would be, what would the integration be? Can somebody tell me what integration means?
Bring together.
To integrate is to bring together, yeah. But I need the mathematical definition rather than the colloquial. And then this is good. And actually the colloquial definition of integrate, meaning to take in, to make all one, it does kind of relate to the mathematical definition. It is kind of to sum everything together. There's I think a more succinct definition. The area underneath the curve. I'm not sure that it's the sum of all of the areas under the curve. Just the area under the curve.
I mean, technically, it'd be the sum because you have all the different rectangles that just get smaller and smaller. So you are summing every slice of area.
That's what calculus integration is.
Yeah.
Sum of areas.
Summation.
Well, okay. My definition is the area under the curve, which you do get there by making the rectangles as small as possible. But actually, I think the whole point of integration is that you can't ever make those rectangles small enough, and integration overcomes that. But you guys have got it. It's the area under the curve. What's the curve? This signal is the curve. Where this line is climbing the y-axis and coming down the y-axis. That's our curve. Back in the olden days, they used to literally print out these spectra from the instrument, and they would by hand calculate the area underneath these signals. They had some like fun paper stuff that they used to do. They'd cut out the shape and then by hand calculate the area. Luckily, we can use computers today. Computers will do all of the integration for us. But computers will give us integrations in one of two ways. Regardless, I'm going to be giving you guys integrations. I'll give you a spectrum, and then above a signal, I will write what the integration is in this form. Signal A, all of those equivalent hydrogens produced by 6 hydrogens. That's its integration, 6H. Signal B, just one hydrogen producing a unique signal, has an integration of 1H. Signal C, 2 hydrogens, chemically equivalent, produce a signal of 2H integration. D, 2H. Signal E, 3H. Now, I will give you guys an NMR spectrum. Let's maybe look back at that methylbenzene where we just had 2 signals. I will provide information on the spectrum that says something like this: 5H, 3H. It'll be written right above the signal itself. Sometimes when those signals are messy and got a lot of overlap, I'll even add a little box that shows you what I'm integrating. The way that Active does it is a little bit closer to how old computers would have done it too. They don't necessarily give you a value, but they give you the proportional size. So 5H, its integration would be shown like this. 3H, the integration is shown like this. And their size is proportional, 3H to 5H. That's a 3 to 5 ratio. It's not quite 50-50, it's not quite 3/4, or whatever. And what you're actually looking at is, what they're saying is, right about here, the area starts to increase, and right about here, the area starts to plateau. This is the signal, and this is how much signal there is. Remember, the y-axis is not of any interest to us. We're interested in the area, which is the ratio of, not the ratio of, the product of the width and the height. Okay, so let's look at an interesting example here and look at how symmetry affects this. This compound is called trans-diphenylethylene, trans-1,2-diphenylethylene.
Is that a circle just a different way?
Oh, I'm sorry. I
I've seen
get
it on
so
the
used to
images.
that. Yeah, the aromatic ring, the benzene ring, its pi electrons are not isolated. Those pi electrons are constantly in resonance in all positions. And so a lot of people just abbreviate the aromatic ring with a circle. We could have just abbreviated it with pH as well. Now, I think you guys would agree that this molecule has symmetry. These two hydrogens connected to the alkene are in identical environments. They are opposite of another alkene carbon with an aromatic ring, and they're adjacent to an aromatic ring themselves. So these two hydrogens, we should expect, give the same signal. And like we've been seeing, it's very common for the aromatic signals to all become one cluster. So I'm just going to call the rest of these B, and because they're symmetric to each other, all of the hydrogens on both aromatic rings should produce the same signal. So what would you expect the integration of A to be and the integration of B? A, not 4, 2H, and B, 10H, 5H on each ring. The problem is that 2H and 10H are proportional to each other at a smaller ratio, which means your instrument would not know to set these proportional to each other as 2H to 10H, but they could set each other proportional 1H to 5H. That's the same ratio, the same proportions, but it's the lowest whole number proportion. That's a bit challenging. So, because of that, I want to look at some common integrations, common bonding patterns that we see. This is not comprehensive, and we run this issue where overlapping unique signals change the integration because multiple signals with multiple hydrogens are all showing up in one place. But when you see an integration of 3H, you can often think of it being produced by a methyl group. Where do you find 3 hydrogens that are all in the same chemical environment producing the same signal? A methyl group. Similarly, when we look at 2H and 1H, 2H we can often think of as a methylene group, and 1H often a methine group. But then we start to get larger than 3, something larger than just what could show up on one carbon. a CH4 group could be produced by two symmetric CH2 groups. I'm going to show that as a dotted line. Now, there is a possibility that the CH2 groups are connected to one another, and that's why they're symmetric. But it's possible that there's a whole world of a molecule in between them. As long as those two CH2 groups are symmetric, they'll produce the same signal, and their signal will integrate to 4H. 5H, not very common, especially not to get symmetry relation, where a 2H and 2H give a signal of 4H. The next most common one is 6H, which is where you have two symmetric CH3 groups. Again, this is a small molecule, but you could put anything in there that separates those CH3 groups and makes them symmetric to each other, and they will give a total integration of 6H.
Would a butane molecule do the same thing?
So butane, I think we looked at butane yesterday. Or we kind of did. Butane has some symmetry between its two halves, two signals, a 6H signal and a 4H signal. But 6H to 4H is also proportional as 3H to 2H.
I think I actually meant ethane.
Ethane, yes, ethane would also have just one signal, where the two CH3s are symmetric to each other.
Can I ask you a question about the symmetry effect?
Yes.
How come there isn't like multiple signals on because like the way that we looked at it before, it was like, oh, this hydrogen's closer to this and this one's closer to
Yeah.
this, so it created different signals.
And well, yes, and that is the prediction. We looked up and saw that we would expect 3 unique hydrogen environments on that benzene ring. And yet, when we look at it, those unique signals are overlapping.
Yeah.
It looks like they're producing, it looks like they're producing just one signal. All of their signals are overlapping. Here's the compound that I'm talking about, trans 1,2-diphenylethylene.
Oh.
And I want you guys to see this big fat signal on the left. That's the signal of the aromatic ring. That's the 5 hydrogens. And it does look like there's many signals in there. But can you distinguish them? No. And if we took the integration, it would be proportional as 5 or 10 to the other signal, 1 or 2. And here's that other signal. What do you guys notice about this signal? It's past 7, which falls out of our predicted range for the alkene. But that's because it's not just in an alkene environment. Once again, it's adjacent to an aromatic ring. Actually now, kind of in both directions. So its signal is getting pushed further left than you might expect. If we went to the computer and we said, all right, I know that this is one signal, and then I'm just going to treat the rest of this as one. The computer doesn't know what to set their integrations to. It is totally arbitrary what value it has. So we normalize the integrations. And normally, you normalize either to a signal that you know already, you know the integration of, or you just normalize to 1. Or I guess normalize to the smallest whole number ratio. So if I took the integration of this signal on the right, and I took the integration of this big overlap on the left, the smallest whole number ratio that I could get the integrations to is 1 in 5. But then I would look at this and say, it's really not common to have an integration of 5. what is producing an integration of 5? And what's balancing that with an integration of 1? So then I can scale up my proportions and say, maybe the molecule has an integration of 2 to 10, because now I can actually get symmetry with a 1H on both sides and a 5H on both sides. Luckily, you guys won't have to deal too much with the symmetry. For instance, if I gave you this and I put your integrations over it, I don't give you the lowest ratio integrations. I give you the true integrations of the molecule you're looking at. Because to me, that is just what is most meaningful. Moving on to our next common integration is the 9H. This really only happens when you've got 3 methyl groups all connected to the same carbon. All 3 of those methyl groups are in an identical bonding environment. That's a tert-butyl group. If you see an integration of 9H, you've got a tert-butyl group in your molecule. And then just to reiterate, overlapping peaks kind of throw this off. Let's look, for example, at 2-cyclohexenol. Cyclohex 2-enol. Man, I get real sick of this. Why does it do that to me? All right, anyways, let's try cyclohexanol. I know that molecule is there because I've used it before. All right, if we look at cyclohexanol, there is symmetry in the molecule. So I would anticipate CH2 and CH2 identical, CH2 and CH2 identical to themselves, but unique from the ones above, and then this CH2, unique to itself. I would anticipate 1, 2, 3, 4, 5 signals, but it looks like I've got 3. I've got this one signal far left, that indicates functional group adjacent. That's the hydrogen bonded next to the alcohol. I've got this one signal here. We'll talk in a minute about how that speaks to being the alcohol. And then I've got this cluster of signals here. I anticipated 3 individual signals. I'm seeing just 1. And so this is going to integrate to 2, 4, 6, 8, 10 hydrogens. Just because it integrates to 10 hydrogens doesn't mean they're all 10 identical hydrogens. It just means that their signals have all overlapped, and now their integration has increased as well. Jamie?
Just like circle back to something earlier. Your hydrogens on the bottom of the ring are going to be more shielded from the oxygen at the top, just because there's more carbon between them.
Correct. So we could do some predictions and say the signals being produced further to the right come from the hydrogens further from the alcohol. And the signals being produced further to the left come from the hydrogens closer to the alcohol. But that would be all we can do. We can't separate those peaks. They've all overlapped.
So if you have like, this is like really specific. If you have like on the bottom of that ring an attached like cyclopentane to make like a 9-sided ring, those ones at the bottom would be very far away from that alcohol. So they'd be much further to the right, right?
I'm sorry. I was distracted. Say it again.
So let's say you had like a 9-sided ring there.
Okay.
Those hydrogens at the bottom of that ring would be much further away from the alcohol. They'd be probably pretty far down that.
Yeah, but remember the furthest it goes is like 0.5, and a 9-membered ring, assuming they're all CH2s, they're all secondary carbons. So the lowest you might ever get is around 1.
That was really specific.
So if all of the signals are kind of overlapping like that, are you just able to assume that it is a ring of some sort, or?
Not necessarily, because a carbon chain might do that as well,
Okay.
where their signals are unique but overlapping. And you might get an integration of 10H, but they're not all identical to each other. It's not like you've got 5 2H groups that are all giving the same thing. Okay, questions? So we looked at number of unique signals, where those unique signals show up along the x-axis, and the integration of those unique signals. We've just got one last thing to talk about when analyzing these signals. This last aspect is the splitting pattern of a signal, which is sometimes referred to as the signal's multiplicity. How many peaks does a signal have? How many times does the signal peak, come back down, but before getting back to baseline, it peaks again? This is a product of coupling. Coupling, quite literally there, means hydrogen atoms coupling their nuclear spins to each other, affecting one another's nuclear spins. And you might think that it's the hydrogen atoms that are all attached to the same carbon that couple, but they don't have any interaction with each other. Hydrogen atoms that are identical to each other have no effect. The coupling comes from hydrogens on adjacent carbons. So we get this equation. A signal's peaks is equal to n plus 1. N equals hydrogens on adjacent carbon atoms. I call them neighboring hydrogens. I don't think I'm the only one that calls them that. I said that like I invented it. N here is for neighboring hydrogens. Not identical hydrogens, neighboring hydrogens. Let's go back to a small example. Butane. We said that butane makes 2 signals, A and B. Signal A would integrate to 6, signal B would integrate to 4. But how would those signals show up? So the hydrogens at B how many neighboring hydrogens do they have? These hydrogens to the right are B. They don't couple. They're identical. But these hydrogens to the left are neighbors. They're not identical to hydrogen. Or excuse me, they're not identical to the B hydrogens. So signal B is produced by hydrogens with 3 neighbors. That means this signal, the number of peaks, is 4. It's not just going to be one nice signal, but instead that signal is going to have 4 distinct peaks. And if we do the same for A, there are 3 hydrogens at each part of A, and each hydrogens have 2 neighbors, the CH2 signals. N equals 2. So A should show up with peaks equal to 3. So some common peaks I want you guys to know. If there's just one peak, this is referred to as a singlet. The signal is a singlet. And it just looks like this. One peak. I guess I want to give you guys the number of neighbors as well. How many neighbors must a hydrogen have in order for its signal to have one peak? Good. We're doing the equation backwards. 1 equals n plus 1, n equals 0. If there are 2 peaks, this is called a doublet. And those 2 peaks typically have an equivalent height. They're twin peaks. How many neighboring hydrogens? Just 1. By the way, is integration anywhere on this table? No. So we don't know how many hydrogens are producing a signal. We're just looking at the number of peaks on a signal. If a signal has 3 peaks, we call this a triplet. The 3 peaks are not all of equivalent height. The 2 outer peaks are shorter than the inner peak. This is because the orientation of the nuclei is affected less often at these higher and lower frequencies, and it's affected more often in this higher frequency. You can get more into the basis of it if you want to. There's a lot of information online and in textbooks. We're not going to. We're just going to recognize this pattern. 3 peaks is always going to be kind of this symmetric shape. Number of neighbors? 2. 4 peaks, a quartet. Similarly, the 2 outer peaks will be of shorter but equal height. The 2 inner peaks, taller and equal heights. Number of neighbors? 3. Now, we can go all the way from 5 to 6 to 7, but I will say that once the number of peaks gets a little bit too large, it gets really challenging to interpret it. For instance, even this signal here, we could look at this hydrogen and how it has 2, 4 neighbors. That means 5 peaks, but can you see 5 peaks on that signal? Not really. So, a lot more than this, or if we go to many or even just complex signals that have a kind of a challenging shape to read, we can call them multiplets. We might not be able to get n out of this. Just gets challenging to read.
Might be a dumb question, but why wouldn't the second have a twin instead of doublet if the third one's triplet? Maybe that's feel like
You what?
like if the second one was twins, the third one's triplet. I'm just wondering like why did they just do twins? Is it twin peaks?
Why don't we call these quadruplets, and why don't we call these quintuplets? And they're from here on, it's called quintet, sextet, septet, octet. But we don't use. I don't know. Doublet actually falls in line with the rest of these.
Yeah.
Twins breaks that.
Yeah.
I don't know that. I get what you're saying, but it's not.
I know.
Sorry.
That's an opportunity. I don't know. Who named it?
And why do we call them only children when we could call them singlet children, you know? All right, one thing I really want you guys to know about splitting patterns, aromatic rings, and alkene hydrogens. They go way too in depth for us to get into in this course. They just get too complex. The same rules that we apply here don't really apply to alkenes, because now the number of neighbors that they have is a little bit different. We've been looking at the molecule styrene. But now the number of neighboring hydrogens is actually kind of different, because these two hydrogens attached to the CH2, attached to the same carbon, they're not identical to each other anymore. So now these two couple with each other, in addition to coupling in different ways with this other hydrogen. So this hydrogen might give signals that indicate that it's got two neighbors, but these hydrogens might also give some indication they've got two neighbors. It also might not look like they have two neighbors. The signals just get too complex. So my advice to you is don't try to analyze the multiplicity within the alkene or the aromatic region. There are some examples where it works out cleanly, and there are many examples where it does not work out well. I will say this. Multiplicity is what gives us structural connectivity. Multiplicity is what tells me how many neighboring hydrogens do these hydrogens have. I have an integration from a signal, so I know if I have CH, CH2, CH3, and now I have a splitting pattern, so I know how many hydrogens are connected to that CH, CH2, or CH3. Multiplicity is what gives us the connective pattern, but as you guys can see, multiplicity is not always easy to interpret from experimental NMR. So then it doesn't always help us try and solve the molecular structure. Another important thing to say, and actually I want to make this kind of a separate point away from chemical shift, integration, and multiplicity. Looking at the hydrogens from alcohols, amines, aldehydes, and carboxylic acids. Some odd things that we'll notice. A heteroatom's hydrogen doesn't couple. I was going to say it doesn't split. Its signal doesn't split. Which means the splitting pattern of a hydrogen on a heteroatom is always a singlet. It does not count towards the neighboring hydrogens in a splitting pattern, and it itself is not split. In this example of cyclohexanol, this one hydrogen that's unique to itself, it has 4 neighbors, the 2 CH2s on either side. It does not count the OH hydrogen as a neighbor. And the OH doesn't have any neighbors. According to this, the hydrogens on a heteroatom never split. So these two signals in the NMR, this one at 3.5 and this one at 2.6, they both integrate to one H. They're both produced by one hydrogen. Which one H group belongs to the alcohol? The singlet, the one that is not split. And which 1H group belongs to the one on the carbon? The 1H that is severely split. Additionally, the aldehyde H never splits, never couples, doesn't have a splitting pattern. Whatever. And this might actually surprise you. For instance, let's look at acetaldehyde. It might surprise you because this hydrogen is on a carbon that has 3 hydrogens on the adjacent carbon. So it doesn't count towards the neighbors, and it doesn't become split by its neighbors either. This hydrogen is adjacent to this carbon, but it does not count towards N. This structure would have 2 singlets, a 1H and a 3H singlet. No splitting. You guys okay with this? There's some other things about shape and location. So the ROH and the R2NH and the RNH2 signals, they don't show up as far left as you would expect. Remember I said that hydrogens that are de-shielded, their signals show up downfield? We would expect that these hydrogens should be very de-shielded. These have a range from about 0.5 to 5.0 ppm. It's a lot further to the right than you would anticipate, given these are hydrogens bonded to an electronegative atom. The reason they don't go through as much shielding, they don't have as much de-shielding, is because of hydrogen bonding. These molecules can be next to other molecules in the sample and they can hydrogen bond. And then lastly, the ROH hydrogen and the RCO2H hydrogen, these can look broad. Rather than having a sharp signal, sometimes the signals produced by these hydrogens are broad to flat. And that's again because of hydrogen bonding. It can change the nature of that hydrogen, changes the nature of the signal that it produces, creates a much wider range of signals given off by the hydrogens. The integration, though, is still the same. You would just integrate over a much broader region than integrating a very narrow range. All right, tomorrow I want to start us off by actually looking at how we can pull out structural information, because we never did get back to that last problem we started with yesterday. So we're going to pull up that NMR spectrum from yesterday. I don't know if I still have it up. We're going to look back at this. We understand a lot more now about the chemical shift, the splitting pattern, and I'm going to give you the integration values as well. And we're going to build the structure based on what it tells us, and we'll confirm the chemical structure based on the 3 structural isomers that we thought could be possible. All right? I'll see you guys tomorrow. Have a good day.